Hey everybody, welcome back to Adventures in Machine Learning. I'm Ben Wilson here with my co-host,
Michael Burke. Hi everyone.
And today we're going to be taking a step back to revisit something that we did a couple episodes ago. There's a blog post by Shreya Shankar on Rethinking ML Monitoring as their second in a series of multiple blog posts that she made that are really prescient. And I think in the future, they're going to become more and more focused on some of the context that she's actually talking about in the blog post. And we're going to handle two additional things we didn't have sort of time to tackle last time. And we'll be going through a couple of pain points, 11 specifically, about that sort of post-deployment phase of a project. Like, hey, you built your baby, you make sure that it's all ready for the real world, you release it out, kick it out of the house, and now what? You can't handle it like you handle a child. You got to still make sure that you're checking in on it. And we're going to talk about some of the ways that can go right, some of the ways it can go wrong, how we can use tools to help out with doing all of those actions, and what we really need to think about when we're building systems that incorporate machine learning. Let's get to it.
Awesome.
Hey folks, this is Charles Max Wood from Top End Devs, and lately I've been working on actually building out Top End Devs. If you're interested, you can go to topenddevs.com/podcast, and you can actually hear a little bit more about my story, about why I'm doing what I'm doing with Top End Devs, why I changed it from devchat.tv to Top End Devs. But what I really want to get into is that I have decided that I'm going to build the platform that I always wished I had with devchat.tv, and I renamed it to Top End Devs because I want to give you the resources that are going to help you to build the career that you want, right? So whether you want to be an influencer in tech, whether you want to go and just max out your salary and then go live a lifestyle with your family, your friends, or just traveling the world or whatever, I want to give you the resources that are going to help you do that. We're going to have career and leadership resources in there, and we're going to be giving you content on a regular basis to help you level up and max out your career. So go check it out at topenddevs.com. If you sign up before my birthday, that's December 14th. If you sign up before my birthday, you can get 50% off the lifetime of your subscription. Once again, that's topenddevs.com.
Yeah, thanks for the intro, Ben. So Shreya was writing this blog, and it's both of us have found it really insightful, and the way she communicates is really effective. So feel free to Google it. But basically, after you productionize a machine learning model, there's a laundry list of potential problems and things that you should be checking theoretically every day, maybe every hour, and no one has time for that. So instead of having a really long checklist, she broke things down into a XY grid, so a 2D grid, where the x-axis refers to the number of components and the y-axis refers to whether it's stateless or stateful. So let's define those really quickly. Single component versus multiple components. You can sort of think of it as the number of modular pieces in your pipeline that could be causing an issue. So if there's a problem during training, well, training is a big term. It has in a simple example, it has a train test split. It has the model training itself. It might have some accuracy calculations. And then within each of those, there's probably lots of modular code. So that would be an example of a cross-component bug or issue or problem. If you can modularize the error down to a single tiny component, well, maybe we'll call that a single component. And this is a continuous scale. On the y-axis, we have stateless versus stateful. Stateful just means that we need to compare current things against prior things. So there's a state to our comparison. And then stateless is more of a just objective, is there an issue or is there not? So example of stateless would be we see negative values in a positively valued column like age. And then stateful would be there is data drift or our code is a lot different than it was a year ago or something like that. So we found this grid pretty effective and really simplifies the checklist process. But we still wanted to get into the checklist. We think it'll be a fun discussion. And there, like Ben said, there are 11 specific problems that are all pulled from, I think, Neptune.ai. They made a comprehensive 32-minute blog post. So if you're dedicated, check it out. But yeah, how does this sound, Ben? I'll take the odd numbers and you take the even ones, and then we'll jump in here and there.
Yeah, sounds good.
Awesome. All right. So Problem number one is data distribution changes. So you can think of this as any underlying distribution of your data, whether it's training or even in the evaluation phase, is changing from pre-production to post-production. And this is pretty common. So it's often termed data drift. So Ben, have you ever observed anything like data distribution changes when working on machine learning models?
If you asked me to list how many times I've seen that, the shorter list would be how many times have you not seen that? So the only times that I have not seen distribution changes would be where humans are not involved in any of the features, where complex systems are not involved. But pretty much the only time where I've never seen drift is in equipment monitoring and industrial processing. Everything else, if the outside world has influence on it, and if humans and human reasoning have influence on it, you're going to have drift. So when your distribution changes, that can be a shift in the mean, and that in and of itself can be a little bit tricky. But the ones that are really detrimental to a lot of problems, like depending on what your implementation is of the underlying algorithm, but when the distribution shape itself changes and it becomes a different family, you're like, oh, I was normally distributed, and now I have this weird Y-bowl distribution where I now have this, what looked like outliers before is actually a massive tail, and the tail is growing. And then it shifts into bimodality because you're sort of splitting off material into another distribution. Now that you have more data, your model's going to get super confused, and it's not going to adapt to that very well if it wasn't trained with that nature in it.
Yeah, that's a really good point. So it sounds like data drift is going to happen, and there's not much we can do about it. Is that what you're hinting at?
We can look for it, and we can alert ourselves to it, but progressing from the start of a project, assuming that it's going to happen, is going to set us up psychologically and preparatorily with our code to say, hey, we know it's probably going to happen. It's going to be relatively inevitable. What are we doing early on in the project to make sure that we can support that change? Does that mean we need code that can retrain itself without manual intervention? Do we need to build in a monitoring system where it doesn't have to be super complex? Sometimes it can be just, hey, write a script that pulls prior values during training versus what we got in the last week, and then do a statistical comparison between those two. Say, how different are they? Or it could be as simple as just look at your features and sort of window them through time. And then within those windows, we're just doing statistical process control. We have like sigma boundaries. If we go outside of where that triggers us to look at it and say, do we need to retrain?
Right. Yeah. And you hinted at a really interesting, and something that I'm personally have some experience with, not a ton, but is essentially looking at the differences between distributions and running hypothesis tests on these changes. So the classic 2-sample t-test looks at the difference in means. And this is really good if the data continue to be normal. But as you hinted, the functional form of the distribution can change quite a bit. And unfortunately, this is super, super important, especially if the model is important, because often at tails of the distribution, we have our power users, or we have our often just really valuable customers, or whatever industry you're in, you're really valuable XYZ. And so even a 1% shift in the rightmost tail of your distribution can have dramatic impacts on the bottom line. So having sensitive tests that don't just look at the mean, but look at things like quantiles. Another one is something called a B-score, not officially called a B-score, but looking at the percent overlap between two distributions. If that changes, we have a problem. So there's lots of statistical methods that address this, but because we're looking at such finite shifts and such tiny shifts in specific areas of the distribution, it's a really challenging problem to detect. And then one final piece, a while back I wrote a blog post about something called Free AI. It is a method developed at IBM that essentially finds weak data slices in your model accuracy. And they have a whole hypothesis testing framework around detecting things like drift. So people are working on it, but currently the solutions that I've seen are mostly around hypothesis testing, or like Ben said, setting reasonable boundaries around a column value. Mm-hmm. So it's a tough problem.
And you can use a relatively clever way if you have a mix of parametric and non-parametric distributions, and you just don't want to deal with like digging through stats models and figuring out which test of the 74 that are in here should I be using, and what family do I need to do here. You can calculate the earth mover distance, which is sort of a brute force way of saying, if I have distribution A, let's say it looks normally distributed, some Gaussian distribution, and then I have another distribution that maybe it's bimodal, or maybe it's exceptionally skewed to one side, or it's a log normal or something that is fundamentally different in the nature of how the data is distributed. Earth mover's distance is, the way I think about it in my head is, how could I, if somebody handed me a picture of a hill and then they pointed to a hill, the picture of the hill doesn't look the same as what they just pointed to. And then they hand me a shovel and they say, hey, go make that hill look like that picture, and then tell me how many shovelfuls of dirt you'd had to use. So that's kind of the earth mover distance. It's like how much of that distribution would have to shift to go to the other one. The bigger the number, the more different they are. And there are actually a lot of drift monitoring tools right now that are proprietary companies use, that they use the EMD, earth mover's distance formula, to determine like how different are these, and pretty effective. But it also goes along with stuff like SPC, where you have this suite of metrics that you're looking at for every feature and your predictions as well.
That's awesome. Have you heard of optimal transport?
No.
Okay. It sounds very similar. I know virtually nothing about it, but it's essentially the goal is to transform one distribution into another in high dimensional space. And I'm assuming they would use something like an earth mover's distance. It's super mathy, but I was like checking it out one day, and it seemed really cool. So just wondering if they were related.
I just cheated and looked it up on Wikipedia. Yeah, this is like the parent family to earth mover's distance. It's the mathematical concept of that. Cool. Today I learned. Thanks, man.
Yeah, glad I could help.
So our second list on a production challenge in this list is model ownership and production. And this one's a point of contention that I've seen working with clients and working as a data scientist in a previous life. And it seems to scale with how big an organization is and how many engineers there are. It really comes down to people asking, all right, we created an ML project or something that uses machine learning. Data science team creates some solution to a business problem, and it's on the checklist at the start of the project. The PM has it as an action item after all the code has been written and we've done our validations. QA passes. The subject matter experts from the business give the big glowing thumbs up of saying, yeah, this solves our problem. This is great. And then in the cross-functional meeting of like pre-production release, everybody kind of looks at each other and says, all right, so who's owning this? Like, who does the deployment? And when it is deployed as a scheduled task or something that's in real time or it's a service, who actually owns the pieces and parts of it? And some people might look at it and say, well, if we have a REST API wrapped around a model, so that infrastructure that REST API is handling, that's definitely the front end team, or it could be the back end team. Somebody's owning that infrastructure. Well, who owns the model that's inside that infrastructure? Who owns that artifact? Is it the data science team? Are they responsible just for retraining that model and then they hand it off? Or do they hand off the code that will do the actual retraining? Who owns that transportation of that artifact to the containers that are running the service? If it's batch predictions that are then being sent off for consumption in a data warehouse, who owns that? Is it data engineering team? Is it data engineering plus data science team? Who actually owns it? And I've seen this work out really well where they'll actually have a cross-functional team that like DevOps owns the process, and they have representatives from data engineering, data science, or ML engineering. And somebody from a software development team that they have a rotating cycle of saying, if there's an issue in this in production, here's the people that all get paged on this rotation, and they'll all figure it out together as this tiger team that assembles to fix the problem. I've seen stuff like that work. I've also seen it work where you train up a data scientist to be a pseudo software engineer, and they actually know all of the components of how to support and monitor and maintain their model. So they can do the DevOps part of it. They understand how to configure K8s to support the pod deployment of these REST APIs. And that tends to work in smaller companies. You don't typically have like a massive company where your engineering headcount is 10,000 and you're just like, oh, we're going to train 3 people to be expert ML engineers for this project. It generally doesn't work out. But it's important to know who is going to be, or the group of people that are going to be owning it, not just that artifact and not just the serving layer, but also the monitoring of it. So when an alert comes in, what do we do about it? Who gets notified and what actions should they take?
Yeah, that's a good point on company size as well, because in my experience, I've mostly worked in mid to small companies. And an example is we had some really great KPI forecasts built, and data scientist who built them was monitoring them, but then left. And then a year later, a stakeholder comes to us and says, hey, the confidence intervals are plus or minus 300%. How do we interpret that? And so one of us had to come in and debug, figure out the whole, all of the production pipeline and figure out how to fix the issue. And theoretically, we would have a team of experts that are dedicated to this specific thing, but smaller companies don't have those resources. So it often falls to one person. But as you were saying all this, I was just thinking it'd be so great if there was an infrastructure that could solve this specific problem and automate the modeling process from start to finish. If only there was something out there.
Hi, this is Charles Max Wood from Top End Devs. And lately I've been coaching some people on starting some podcasts and in some cases just taking their career to the next level. Whether you're beginner going to intermediate going to advanced, whether you're trying to get noticed in the community or go freelance, I've been helping these folks figure out how to get in front of people, how to build relationships, and how to build their careers and max out and just go to the next level. So if you're interested in talking to me and having me help you go to the next level, go to topenddevs.com/coaching. I will give you a 1-hour free session where we can figure out what you're trying to do, where you're trying to go, and figure out what the next steps are. And then from there, we can figure out how to get you to the place you want to go. So once again, that's topenddevs.com/coaching.
I mean, there are a number of companies that offer these solutions. The company that I work for has a pretty good solution. We heard about some aspects of that last week on the episode with the ML Flow team that handles some aspects of the ML Ops needs. When we go from registering a model, though, and then pushing it to production, tooling is amazing. And tooling is getting better to fully automate everything from data ingest to registering, common features that are going to be used across multiple projects and across multiple teams in a single place, and making it reproducible. And you can set monitoring, but tooling only gets you so far, and tooling will help you automate away or ease the process of doing something. But once something's in production, no amount of automation is going to ever automate out humans from this process. There's so much nuance for any project that's in production. You really want people looking at it. You want brilliant people's brilliant minds evaluating and being suspect of whatever's coming out of that service and saying, is this what we want? Can we make it better? How is it doing right now? How did it do compared to 3, 6, 9 months ago? And what are we going to do to make it better? And so tooling's great, but it's never going to replace a human.
Good to know. We'll still have jobs in the next couple of years. Moving on to point 3, we wanted to discuss a train serving skew. So what this means is there's a difference between accuracy or performance in training versus when it's productionized. This is more like just a big symptom. And I almost wouldn't call it a challenge. I would call it a symptom of a challenge. For instance, if our data distribution shifts then our train serving skew will be problematic. So, Ben, have you seen, I'm sure you've already said you've seen this, but could you give one specific example of when training was very different from serving?
I mean, I've got an amusing one, and I definitely cannot tell you who this is. Cool. I don't think they would appreciate it, but a company that was involved in moving goods across the world. So logistics. And their data science team could only get a data dump from the data engineering team, a one-time dump, because of the sensitivity of the data and how things were siloed. So they created this development environment for them to go and build a model to solve this particular problem. They got 6 months of data dumped to them, and they were told, hey, this is what you got. And it's a lot of data. Based on the nature of that data, it was truly an obscene amount of training data for any ML model. We're talking many, many terabytes of data we're put in this development environment. Nobody sat there and thought about, hey, should we have sampled over a period of, say, 6 or 7 years of data and still had the same data volume, but think about the temporal aspect instead of, hey, you guys asked for 10 terabytes of data. That's 6 months of data. Here you go. Here's all the data. So they had a really great model that they had built, and it was basically trained on 5.5 months of data, and they left out 2 weeks of data to be a holdout. So it was never part of the test set. It was just their validation. So every model that they were testing was always validating against this 2 weeks of data it was the most recent data that they had. And they really did a fantastic job of running through all of the validations that you could ever think of. I mean, they had a dozen different metrics, even custom metrics. They had stuff where they're estimating what the business impact was going to be based on this model with simulations. And then they were running like, hey, what happens if this happens? And generating all this synthetic data to throw through the model and then manually validating it and running their own scoring. And it was great. It was like how you're supposed to build an ML implementation. They released it to production about a month later. Complete garbage. Like so far from useful that it was like they actually intended to make it bad. And I remember sitting in a meeting where they're going over this and they're like, we think there's something wrong with your platform. I'm like, no, I'm pretty sure we're not. I think this is the seasonality thing because we're in the holiday season right now and your training data didn't have November of last year in it. And the look on everybody's face in that meeting where they suddenly realized that, oh no, he's right. Like, that's why this is bad. Yeah, it was tragic. Luckily, they had written the code in such a way that retraining took about a day and a half because they had everything written properly and they fixed the problem by that Friday. And this was like a Monday when we were discussing it.
Wow.
So they knew what they were doing, but you could definitely get this if you're not thinking through what is that model actually seeing. It's not about the volume of the data. It's what data is it seeing during training.
Yeah, and this sort of leads into the next point, which is model and concept drift. Would you call this concept drift? Or, I mean, it's literally data drift, but it is due to a lack of a comprehensive training set.
Yeah.
So, I mean, I don't know. What I was sort of hinting at there is this could have been avoided if they had thought about it a little more.
Yeah, they weren't even thinking because another team was handling their data acquisition and they had no power. They didn't have access to prod data. They didn't have access to the training data, period. So that can happen in really big companies where, you and I, we both have worked for mid-sized companies, worked for startups. And when you're even in a mid-sized company, data science team generally has access to most of the data. You don't have like prod data of, you shouldn't have prod data as a data scientist, like actively being able to read and write in prod. If you do, please tell your CTO that something's wrong. But at a massive company, you're at a Fortune 500 company, data scientist is probably 10 to 12 humans away from being able to even ask permission to see prod data, let alone be able to access it.
Yeah, and just one other fun anecdote about that. So often we see this phenomenon where in a single evaluation set that's public, So for example, the Mints data set or Stanford has a question and answering data set. We see models really, really overfit that given data set because hundreds, if not thousands of people are trying hundreds, if not thousands, or probably tens or hundreds of models, not thousands. But the point is there's a lot of volume that is being trained on that specific set. And so when you create models on that set, they perform beautifully. But the whole point of a model is to generalize. And so often with those training sets that are sort of like ImageNet, for example, for image classification and all sorts of other things of that nature, they look really great in the training stage, but they don't generalize super well and solve the grand problem that they were hoping to solve. And so that's just another example. If you have one data set that you're optimizing the crap out of, well, will it generalize is not a guarantee.
And that's really the crux of what people should be focusing on when they're training a model is like, hey, we're all geared towards, and we talked about this a couple of weeks ago, we're all geared towards minimizing loss in the test data that we're evaluating a model against. And if you're not super careful about what features you're throwing into your model and what data you're throwing in for it to learn from, it can learn patterns and optimize on things that you would rather it not do, or reality would rather it not do when it's exposed to the real world data that's coming in. So I've seen people counteract this model and concept drift concept. And 3 and 4 that we're talking about on this list are kind of, just as you said, they're kind of related to one another. But to counteract this, I've seen people go into simulation mode where it's a shadow deployment of something, even if it's in batch. You just say, hey, for this entire sprint, this 2-week sprint, because this project is so important, we're going to kick this prediction off every day, and nobody's going to use it except the data science team. We're going to run it against prod data and just see what the results are. And the time that you do that action is usually predicated on what is your latency for receiving ground truth. So if you're trying to predict fraud, for instance, and we work at e-commerce and we want to determine if all these transactions are fraud, we can use holdout validation for that in order to get like, hey, are we using the right model, or is it tuned properly? That's great. But the only way that we're going to know whether it's doing its job is to have it actually predict on real data in real time, write the results out, and then we wait 2 weeks or 3 weeks, however long it takes the fraud detection team of humans who are experts at this to classify activities as fraudulent. And then we see, did it actually catch this correctly? And then we can present that to the cross-functional team and the business stakeholder and say, all right, we did this super secret shadow deployment and validated against your team and how they're doing it. And here's all the things that were detected that they classified that our model didn't classify. And here's the stuff that we classified that they didn't classify. Which one do you think is correct? And then set a couple of weeks of sessions of people evaluating that until everybody's comfortable and saying, yeah, let's use the model as like a first stage and then send that on to the people to validate.
Yeah, that's an awesome segue into point 5. We'll skip point 4 because we've touched on it a bit. But just thinking about how to interpret black box models and building trust around those predictions, a really effective way would be to benchmark it against current, whatever the process is, current processes, and figure out where is it doing well, where is it doing poorly, and then telling some stories around each of those areas. It really helps stakeholders sort of get an intuitive grasp of what the model is good at, what the model is bad at, and it makes it seem almost more human. Like, it will make mistakes. It will make mistakes in a pretty systematic way. It might make some crazy mistakes here and there, but overall, we should see a total accuracy that is better than the current system. So how important, in your experience, how important is it that black box models can be explained?
Entirely depends on, not entirely, but it mostly depends on what your industry is, how much money is on the line, and how dangerous is it if we get it wrong. Now, to break those 3 things down, the first one, industry. Some industries are required by not so much law, but just regulations. So there's regulatory agencies saying, hey, if you're messing with these things, we need explainability, and you can't actually deploy things to production if they can't be explained. So the black box model idea is just out the window for them, which isn't to say you can't use stuff like neural networks or things that are very challenging to explain. Good luck explaining support vector machines to a layperson with just looking at the actual model artifact. It's kind of tricky. So that's why a lot of those regulated industries will use tree-based approaches, because you can just dump the tree and somebody can look at it. If it's a forest, you can dump the forest and aggregate the trees and kind of say, this is kind of what it's doing. You could use SHAP, you could use Lime. These things approximate explainability of black box models, but some industries you just can't get away with things. And then the second one, how much money is on the line? And that relates to, are you touching something that a business really cares about, i.e. money? If you're doing something that can directly impact revenue or profit, then people are going to want to know how it works. They're not going to really care when it's making money. You need to prove that it's making money. That's attribution analysis, and that's another super critical part of any project. But where people are going to get really annoyed with the data science team is when something that was making money is no longer making money or is losing money. You want to see the most amount of anger that can come towards a data science tech lead. Have your model that was creating 20% sales lift now create negative 5% sales lift. And you'll see just how furious a CEO and CTO can get, and COO can get behind a closed door. Been there, experienced that, not fun.
Hey folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
So if there's a lot of money on the line and it's really important to the business, you should approach your potential solutions that you could use to solve that problem, keeping that in the back of your mind. Like, hey, I'm probably going to have to explain how this thing works if it goes belly up. And nobody at the top is going to have any faith in you as a data scientist or an ML engineer if you kind of just shrug when they say, how does this thing work? And you're like, I use train and test, and then I push the magic go button. They're going to be like, well, how does the algorithm work? And you're like, I don't know how it does what it does. Some really smart people at Google and Facebook thought this stuff up, and I don't even think they can explain it that well. So that doesn't say, hey, you can't use some of these more advanced techniques and frameworks. It means strike a balance between what your business is comfortable with and how important the project is to determine how important explaining it is. And then, that third part of how much do you have at stake with this thing? If it's not money, it could be, you could do something, or your model could be interfacing with customers, or it could be interfacing with other businesses. And if it's something that's directly visible, the output of this, that based on its quality or lack of quality, either builds or erodes trust in your company's brand or image, be very careful about knowing how it's doing what it's doing, and how you can, the more explainable it is, the faster you can fix it when something goes wrong. So that would be my point of advice on that topic.
Yeah, that's a really good point. Especially the final point about, even if it's not important for company understanding, it might be useful for your understanding, for improving the model, for iterating, and for just being able to debug things when things go wrong. If you know that your model relies heavily on this variable and suddenly this variable goes out the window because there is a giant worldwide pandemic, well, you can maybe iterate and improve a lot faster if you know that's the case. Mm-hmm. And so the next point is considered adversaries. That means evil people are trying to mess with your model. We should probably skip that because that's a whole other, that's a full podcast in itself.
Speaking of that, we just hit the halfway mark on this list. We definitely have an entire episode to get through for the other half of this list. So
all right,
we could probably start the next one where we do a panelist off at this, and we'll be going through that concerted adversary, and we could share some stories that we've seen or heard about about crazy stuff where somebody is attacking a model either to break its training or to figure out how it works. And it is something that if you have a REST API and a model exposed to the public, you should be thinking about, depending on your industry. But we'll cover that stuff in another episode that'll be coming up in the next couple of weeks. Next week, we'll actually have a guest on where we'll be asking them, why are they famous? And what sorts of amazing stuff have they produced? And we'll have a good time getting back to that format. And yeah, so until then, and until that next episode, this has been your co-hosts, Ben Wilson
and Michael Burke.
Thanks for tuning in, and we'll hope to see you next time.
Have a good week, everyone.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more.